for warm-up number 1. And then question 2 of the warm-up should be starting at vertex A, not D. But okay, DFS. Who wants to tell me what it does? Like, first, like, what are we doing when we run DFS? It's kind of it's a vague question, but what do we do? Why should we run DFS instead of like picking random nodes? Sure, there's lots of applications. So it's like, oh, what if I want to find paths? There's also like it's a really open-ended question. Like DFS is used for a lot of things, but generally, the thing that you should like remember is that graphs can be used to represent a very wide range of problems. So, for example, if you guys have ever connected to the internet, like have you ever thought to yourself like, how does the internet work? Like, how am I able to ask Google for a web page when Google is like not even in my city, and I get like fractions of a millisecond of response, you know? And it's a whole graph problem because you have a bunch of like routers that bounce packets off of each other. Take 168 for more, but like graphs are very important in that they can represent a very broad range of problems that are very interesting. So you have networks, you have maps. You guys are going to implement maps in Project 3. So to motivate it, and also if you take like 188, you can do, there's like search spaces, but to motivate graphs, you should just, for DFS, it's really just like, I want to explore all of my nodes, and I want to do it in a certain order such that you're kind of like going depth first, right? You're going to go deep into the graph instead of like doing breadth first. So the sort of traversal you're going to do is that if you start from A, you're going to like kind of follow as far as you can go, and then like you backtrack, and then you follow as far as you can go, and then you backtrack. And then you're like, okay, this is how far I can go. Whereas for like BFS, you do like breadth first, right? You're like, I want all of my neighbors. And that might make sense if you want to do like shortest paths. So if you remember from homework 3, if we do like a simpler version of homework 3 where it's like, I want to find the least number of moves to get to a solution, you want to use breadth first search because you want to kind of like stay close to your start. And then you want to like search in there. So it's like finding optimals. Okay, so yeah, breadth first search looks something like that. And, no, it looks like that. But okay, let's actually do DFS. So what you're doing is you have this concept of a fringe. So do you guys remember fringes from lecture? Yeah? Yeah, now? Who knows what a fringe is? It's pretty much like, this is where you store nodes. I'm going to use nodes and vertices like interchangeably. They mean the same thing. They just mean these bubbles over here. So you're going to store nodes that should be visited. So if we look at number 1, it's like, let's do DFS starting at vertex A. So we want to first start at vertex A. And what we want to do is, yeah. Oh, whoops. B to C? Yeah. Okay. So what we want to do is we want to start at A, and then we want to on-queue nodes such that we're sort of like digging deep down. Like if you imagine the ground as like a graph and A is at the top, you want to like dig deep down, like you want to follow like, think of like a tree's roots. You want to like follow the first root until you can't follow it anymore, and then like you backtrack up. So the way we're going to represent a fringe for DFS is with a stack. So when I do DFS, like the algorithm is really just, we're gonna first pop off a vertex from the fringe, and then we're gonna on-queue, or we're gonna push all of the neighbors to this fringe. And then you're gonna repeat step 1 until your fringe is empty. So that's like bare bones algorithm for DFS. So let's just run through it on this example, where we start with our fringe. Let me copy this graph. Okay. Does anyone have any questions so far? Okay. Well, oh my God, that's scary. Okay, back. Okay, so let's start DFS at vertex A. So I'm gonna have our fringe over here, and for our fringe, I'm gonna put A on it, right? Because we're gonna start there. So the fringe, remember this is a stack. So when I pop something off of the stack, first I'm gonna pop off A. So then that means the first thing I have visited is vertex A, right? So then what do I add onto the stack if we're gonna break ties like alphabetically? Like we're gonna alphabetically visit. Yeah, we're gonna put B and C on the stack, but because it's a stack, we're gonna put C first and then B because we wanna. It's probably better represented if I draw this like up, in the upwards direction. So we want to put C here and B here, right? Because when you pop off a stack, or you pop a stack, you take the top, right? And we want to alphabetically visit the lower alphabet, earlier alphabet. You want to visit B before C, yeah? So that's the way the alphabet goes. So is this good so far? Yeah. Okay. So then another thing you do in DFS is that you don't want to visit vertices more than once. So we kind of have to just keep track of vertex, like nodes that we visited. So here I'm just gonna highlight A to denote that we visited it. Okay, so then now which one do I pop off? Yeah, we pop off B. So we visit B. And then we put all of B's neighbors on there, right? So B has C, E, and D. So it's kind of weird like when you do this in the stack way, but you are going to want to visit C before E and D. So what you can think of this as like you sort of you like on-queue all of the neighbors again. So you just put E, D, C. Yeah. So then now we pop off C, and then we visit C, and then we put all of C's neighbors on, right? So what are C's neighbors? E and F. So then we're going to put F and E, and then what do we pop off next? Yeah, we pop off E, and then we visited E. Okay, do we have any neighbors to on-queue for E? Yeah, we can put G on there. So then we pop off G, right? Oh, and I forgot to write the order. So it's A, B, C, E. Good so far? And then once you start running DFS a lot, you can just sort of do this in your head where you're like, I want to do that, But for now, it's good to just draw out how the stack grows so that you start building some intuition for how to run it. Okay, so we pop off G. And we have visited G. And then now we don't really have any more like children to add, right? So now what's the next thing we can pop off? F. So like if you look at the stack, F is still at the top. So if we pop this off, we'll visit F. And then we'll look at D. So like D is the next thing. We'll pop it off. And that is your DFS order. And B and Z will pop off the stack, but because we visited them already, they're not going to do anything. Yeah?
Why don't you pop D before F?
Why do I not pop D before F? Because, oh my gosh. Okay, we have to draw the traversal again. So we go A, B, C, E, G, okay? And then, we're still, oh, actually, yeah. You're right. We should be, well, hold on. A, B, C, E, G, backtrack. Yeah, it should be F and then D. Wait, yeah. Wait, so I'm right. Yeah? Okay. It is easier if you like draw the path because you're pretty much saying like, let's go as deep as we can, and then if we can't go any deeper, let's backtrack and see if we can go deeper from there. Does that make sense? Okay. So then BFS is exactly the same as DFS, except instead of a stack, you have a queue. And we'll see how that works. So let's run some BFS. Okay. So we're also going to start at A again, but now we have a queue. So when I take A off the queue, I'm going to add its children, right? And now because I want to visit them alphabetically, I'm going to add B and then C. Yep. Okay, so then because queues are first in, first out, B is first in line, so I'm going to visit B. So we're going to put B here. And then we're going to put B's children on the queue. And then B has the children C, E, D. Yeah? Okay. So let's mark our visited nodes. So we visited A, we visited B. And then now we pop off C, or we DQ C. And C has the children E and F. And remember, we're never going to visit a vertex more than once. So that's why I can have these multiples, like these duplicates in my queue, because they will end up getting DQ'd, and nothing's going to happen because we're going to visit it already. Okay, so we visit C, and then C has the child F, and then we're going to pop off C again, but C has already been visited, right? So we don't have to do anything. Okay? So then now we just pop off E. Huh? Oh my gosh, I can't alphabet. Sorry, guys. Okay. Yeah. So D and E, pop off D, visit D, and D has G. Okay. And then we pop off E, visit E, and then E has, I'm missing a couple duplicates. So we added G, and D also was pointing to E, so we added E and G. Okay, so we popped off E, and E is pointing to G, so we just add G again. And then pop off E again, we already visited it, so do nothing. And then here, we pop off F, so F is here. Then we added another G over here. And then this, we do nothing because we visited it. And then we can DQG, and that's our BFS. So instead of using the queue, you can also just visualize it as I'm trying to be very conservative with how many edges I'm using as I'm like visiting all of my vertices. So like here, it's like I want to do this one and this one first because they're the closest to A. And then now I want to do the closest, because we're breaking ties alphabetically, I want to do the closest ones to B over here. And then I want to do the closest ones to C. Does that make sense? And then eventually you're like, okay, I want to do the closest one to D. So that's BFS. You can kind of think of like you're trying to create like a tree that's like rooted at A, and you're trying to just find all of the nodes that are like closest to it. And the thing that you should remember about DFS and BFS is that they visit the same number of nodes, and they could use the same number of edges while you're like traversing. So the runtime of is what? Yeah, B plus E. So a realization here to make is that DFS and BFS aren't that different. It's just that you're changing the order in which you're visiting the vertices. Does that make sense? Yeah.
And this is the runtime for both?
Yeah, for both of them.
Adjacency matrix representation and then adjacency list.
Yeah. So for both of them, because like you're gonna visit the same number of vertices, like in the worst case, you're gonna have to like kind of like look at all of the edges, right? And then like all the edges could be pointing to something that you visited before. But it's the same because you're visiting the same number of things, but your order of visiting is different.
How can you access D from C? I know like you're just going down the queue, but I'm just like sort of confused about the traversal and following the paths.
What do you mean?
From C to D.
From C
Yeah.
to D?
Yeah.
So because so how do we go from C, like after, how do we go from C to D is what you're asking. Like how do we make that hop? So remember, because you're using a queue, you're gonna on-queue like these children first, or these like neighbors first. So then after you visit C, it doesn't matter what you like put here, you're still gonna like go in priority of the queue. And that's why BFS has this behavior of
So
where,
the priority of the queue takes precedent in that case.
well, it's like the ordering that you put your nodes in
Okay.
is what matters. So like this isn't exactly gonna follow the way DFS does, where it's like, let's just take the next adjacent edge. This is like kind of going by levels, so you can have a hop, right? Like once you're done with a level,
Right.
you hop to the next one.
Yeah, because that's the level you want.
Yeah.
Right. Because and you already like checked for D and
I was tired. Okay, let's do number 2, which is a regex problem. Regex problems, I just suggest that you write down the rules. Oh, I have 2 people here. They might interject. But for regex problems, you might just want to write down the rules for like what the tokens mean, and then kind of refer to them on your cheat sheet so that you don't have to panic about memorizing all of these rules. They'll just be on your cheat sheet. So let's do number 1. These are pretty straightforward. We're not going to throw anything really ugly at you. We just like expect you to memorize like that one table that Hug had on the first, like on the regex lecture. So when we parse regex, we just go left to right, and we kind of just like convert all these tokens into what they should match. So here we have match a set, HELLO, and what this means is that the letter we're matching can be H, E, L, L, or O. So you shouldn't take this to be match the word hello, it should be match one of the letters in hello. So this could be, that's what it means. And then we have \W, and \W means any alphanumeric, this is actually not in scope for the midterm, but \W means that you can have any alphanumeric or underscore character, so that's what it's matching for. The plus means to match the preceding token and like 1 plus times. So we can match the word 1 plus times. We can match any alphanumeric character and an underscore 1 or more times. So we could do something like www underscore, and that would be a match, and so on. And then RLD is just like match RLD. So when we read this, it says the first letter is either H, E, L, L, or O, and then we can have anything in the middle that's alphanumeric or underscore, and it has to end with RLD. So we can parse this first and eliminate the ones that don't match this first expression. And this one matches because H is a part of this set. This one matches, but this one doesn't because S is not a part of the set. So this one also matches, and this one also matches because O is a part of the set that we're matching for. So now we go on to this part, and over here, you're really just going to eliminate words that do not have alphanumeric characters or underscores after the first letter. And all of these don't violate that, so this is going to match every word that we have left. Now, if we go to the third expression, it wants us to match for the last 3 letters being RLD. And what do we know? All of these are ending with RLD. So all 4 of these match. Okay. The next one is a little bit more complex, but it's really, regex is pretty straightforward if you just break it down left to right. So again, I'll just translate what all of these characters mean. So we have A to D, 0 to 9, and what this means is match any character in the set A, B, C, D, and the number is 0 to 9. So if the first letter, or actually in this case, because we have a plus after, it says match 1 or more of the preceding token. So that means we just want to match 1 or more of A through D and 0 through 9. And what that means is we can just go ahead and eliminate all of the words that don't start with D, with A through D or 0 to 9. And over here, none of those get eliminated because D is a member of the set, 6 is a member of the set, and so is A, 0, 9, and 4. So then the next one we have to match for is \\. In regex, \/ is the escape character. So when you do \\/, you're actually saying match for the \/ character. So this kind of makes this problem a little easier because we can eliminate 4 words now. because 4 words don't have, or 4 strings don't have a backslash character in it. So over here it's match one or more of these tokens in the set, and then after that we need to have a backslash. So these all don't have backslashes, so even though they match the first part, we can just eliminate them because there's no backslashes. And then we're left with these two. So now we're kind of like at this part in the string. And we move on. So notice that because the backslash character doesn't have a plus after it, we're only matching for one backslash. However, we look at the second expression, and the second expression is telling us caret backslash d. Backslash d means match for any digit, and the caret means not. So what it's saying is make sure that the next element is not a digit. So the next character is not a digit. And because we have the special set token here, it's saying make sure that the next 2 to 5 characters are not digits. So what this reads as is you have some token here, and then the set of like 2 numbers after it is saying match the previous token for 2 to 5 times. So when we do that, we'll say, okay, we don't want a digit for the next 2 to 5 letters. And over here, that works because we have 5 letters that are not digits. And then here, this works as well because we have 5 letters that are not digits. So that means after matching the whole expression, we have this left. And that's number 2. Well, let me recircle that. Okay. Stop. That's not the stop button. Who doesn't? Who wants me to like go over pre-order, post-order, and order? We'll do it briefly. But first, let's make this tree. So, because the BFS traversal yields the sequence genius, we pretty much have to put genius into like a binary search tree with this constraint, such that like, you know, the height of G has to be the root, and E has to be like either above or at the same level as N. Does that make sense? Yeah. Because when you have a BFS traversal like this, remember BFS is like in order or level order traversal, right? So it's like it's basically telling you the order of like the levels like left to right. Yeah. So I already told you guys G is at the root, right? And then E is going to be at like a level lower than the root. And because E is less than G, we're going to put E over here. So where does N go? Yeah, N goes to the right. And then what about I? To the right and to the right of E. So remember the binary search tree has this constraint where everything on the left of like a parent node has to be less than it, right? So we know that the level is going to be here, but like there's like 4 slots, right? So which one should it be? Yeah, to the left of N. Why? Because I is greater than G, so you still have to go to the right. Okay. And then what about the U? Yeah, the U goes to the right of N because like U is greater than G, which is also, and it's also greater than N. Okay? And then where does the S go? To the left of, yeah, to the left of U. So notice that this is still a valid, like the BFS traversal we're given is still valid because we do G, E, N, I, U, S. So like I'm working in this direction, right? So it's still, we're still good.
Did they give you the alphabetical order in the test?
So they say that a binary search tree, this is a binary search tree, right? So I could have like Genius look like this, but then that wouldn't obey the rules we set for a binary search tree. Yeah.
Because I don't remember that eyes.
Yeah, alphabeting is hard. I mean, I forgot that like D was less than E, right? So, but you pretty much have to like when you're given this this order, you in the case of the binary search tree, it's almost like the insertion order because you're like it's sort of like the insertion order, but in this case it was because you have to basically make it a binary search tree, but also obey the fact that like we have these like constraints on where the position vertically of like these letters should go. Did that make sense? Any questions? Okay.
Could you have done like GEN and IUS, like in the third row? As in like I and U would be children of E.
I and U would be children of B. No, because they're greater than G.
Oh, it's a search.
Yeah, it's a binary search tree. If it wasn't, yeah, you could. Okay, so pre-order traversal. First, let me go through the 3 types of traversals. So there's pre-order, there's post-order, and then there's in-order. And the most compact way to describe this is that, like, let's say I have a function to call when I visit a node. So in most cases, it's like, let's print the node, okay? When we do a pre-order traversal, we're going to print, and then we're going to call f on the right, on the left, and then f on the right. When we do post-order, we're going to do f on left, f on right, and then we're going to print. And then when we do in order, it's going to be f on, pretend f is like a function. F on left, print, and then f on right. So these recursive calls might actually be really hard to visualize because you're kind of like, oh my god, I have a lot of frames open in my head right now. So the way that Hug goes about it is that you should just remember, like, so if we're going to do the pre-order traversal of this, what you do is you kind of draw like a path around the tree. And the intuitive thing about this path is that it's like, oh, I'm going to go to the left, right? And then over here I'm going to return, and then now I'm going to go to the right of G, and I'm going to go to the left of N, and then the right of N, and then the left of U. Do you guys sort of see like this traversal? It's kind of like I'm calling left, and then like I'm following all the way down to the left, and then I'm going to come up, and then call on the right, and then left and the right. Yeah? So for pre-order traversal, you're just going to print the nodes in the order of to the left of like the path. Now, intuitively, why does this make sense? Because when you're on the left of a node, you're pretty much, it's like your first time visiting the node, right? You haven't done anything. So that's kind of the intuition behind it, where it's like you're walking along all of these nodes, and whenever you pass the left of it, you have, it's like your first time visiting. You haven't made any calls on the children. So that's why it's pre-order. So then, pre-order, right? Because we print and then we make the calls on the children. And that's the same as like looking at the nodes to the left of the path. Yeah?
Pre-order is different from level order, right?
Yes. So,
But it prints the same in this case?
in this case, yes. It prints the same. So yeah, don't confuse pre-order and like level order to be the same. There's like 4 different traversals: pre-order, post-order, in order, and level order. So in this case, because I walk to the left of my path, I get G, E, N, I, U, S. Yeah? And this can also just be seen if we print G and then we visit E, we print E, right? So you have G, E. And then you go back up, you visit the right, and then you print N, so N. And then you print I, and then you go back up, and then you print U, and then S. Yeah. So then that's pre-order. For post-order, now it's going to be when we visit the right of a node. Because it's kind of like you have to go to the right of the node to be done, because you have to like visit the left and the right child, right? So over here, like if we're walking along this path, oh here I'm done with E, and then I'm done with I, and I'm done with S, and U, and N, and G. So it's kind of like we finished taking a walk around a subtree. And then once we're at the right, it's like we know we visited the left and the right. Is that kind of giving you more intuition? Yeah, no? Okay. Any questions? Okay, so in order is when you visit the bottom of a node. So that's when you visit E, and then I, and then N. Oh, my bad. E, and then G, and then I, and then N, and then S, and then U. Yeah. So it really is just like kind of imagine you have like children coming out, and then Pre-order is before you visit any of your children. In order is after you visit the left child. And the post-order is after you visited the left and the right child. Yeah? Okay, cool.
Is in order on a binary search tree always guaranteed to return?
Let's build some heap intuition. This problem is hard. Like, it's hard. It's okay if you don't instantly, like, get a counterexample to just, like, pop in your head. But I can go through, like, sort of, like, the high level, like, what's wrong with the approach of syncing all the nodes in level order. So I'll just draw you a heap here. And I think just the key realization to make is that for number 1, when you sync in level order, it means you're going to sync this one down first, right? And when you sync this one down first, it's the equivalent of like locking this node into place, because you can never sync upwards, right? So it's like after you sync this node, you can no longer like get the rest of your nodes and like sync them up. So is that intuitively, like, I don't have a concrete counterexample, but intuitively does that make sense to you guys? Where it's like, once I sync this node's position is like locked forever, because nothing can ever come back up to it. Because like we will only ever sync these nodes, and those nodes, like when you sync them, they can't swim upwards. So then, given that counterexample, that just means like your nodes have like a mobility of like +1 to the root. So I can give you an example where I have like a 1 here, and then I have a 6 over here, and then I have like a 0 over here, and then I have a 3 over here, 5 over here. This stuff can all just be trash. Doesn't really matter. Like, they can be any variable. But the point I want to make is that when I sync this 1 doesn't sync at all, right? So, like, when I sync the 1, I've effectively locked this 1 over here. And even though this 0 belongs at the top of the min heap, so pretend this is a min heap. Even though the 0 pretends at the top is like going to stay at the top of a min heap, it's never going to move upwards because we can only sync nodes down. Are we good with that? Yeah.
Why wouldn't it?
Because we try to sync the 1 first, right?
Yeah.
We can't sync it. Okay. We sync the 3. Sure, something happens on this side.
Does it only check?
Right. And then we try to sync the 6. And you just get a swap here. But you actually want to swap the 0 up here, right?
But does it only check the children?
Or no, it's not you only check the children. It's not like because you start at the top, like you can check children. Yeah, so yeah, you only check the children when you're syncing because you can't sync upwards.
Doesn't it have to be a BST though?
Huh?
The title says BST, so it's kind of confusing.
We have a complete binary tree that is not a heap, and we wish to heapify it.
Yeah, but the title says BST.
Oh,
So it's
you're
like,
right.
What do we do?
Okay. Well,
You could just do
I
like,
mean,
you could just do like 4, 2, 6, 1, 2, 5, 7. Like
4,
a 1, 2, 3, 4, 5, 6, 7.
2, 6,
Yeah, 1, 2,
3, 5. Okay. Cool. Ah, it's BST.
Yeah.
All right. So another counterexample is if we try to sync the 4, yeah, your 2 is gonna get locked into the root, right? So it's gonna look something like this. And then 6, 5, 7. So when we sync the 4 syncs all the way down, but now we can't sync the 2 because we're like done with that position. And even though we wanted to sync, like we want the 1 to swim up, it can't happen. No mobility. So okay. Now for number 2, do you guys think it'll work or not? Why?
This one, children like to go up, so I guess it's got the mobility to go up, and then
Right.
the top one can go down.
Yeah, basically like an easy way to see this is that like this is what you do when you insert into a heap, right? Regularly. Like when you just insert items into a heap, you like start at the root and then you add 1 here, swim it up, you add 1 here, swim it up, add 1 here, swim it up, add 1 here, swim it up. So Like that's a generally this is how a heap insertion works. But also it's just that because you're swimming up in level order, pretty much all of your nodes at every position will have a chance to like move up. Like you don't end up locking nodes away. If that. Like your top position never ends up being like locked. Because you'll always be able to swim up the rest of your nodes, and they might make it to the top. Any questions? That was kind of like hand wavy, but you can just think of it as also this is like how do we insert into a heap? We do exactly that. Okay. All right. Swimming all the nodes in reverse level order. Do we think that'll work? No? Okay. Does anyone want to give me a counterexample? Anyone? Yeah, like you do like right to left, and then you do it repeatedly. Yeah.
Oh, this is right, left, like from bottom to top.
Yeah, so right to left and bottom to top. Yeah. Yeah, do you have a counterexample for me?
I think.
Okay.
So I have 7 as the root.
Okay.
Then I'm just gonna read it in level order.
Okay.
So 7, 6, 2, then 5, 3, 4, 1.
Okay, so let's try swimming up in reverse level order. So the 1 is going to swim up here. Yep. It's going to get kind of messy. The 1's going to be here. One, and then 7 goes here, right? And 2. Okay. And then we're going to swim this one up. So these are going to switch places. 4, 7, oh, 7, 4, and then this is going to swim up and switch places with the 6. What did I just put there? Okay. Okay. 3 and 6, and this is going to swim up and look here, we have a bad node. So over here the problem is again that like you're locking positions. So in this case, because you're swimming up and you're doing it like bottom to top, you're kind of like locking this position away. Like you can, once you swim this node up, you cannot change the number in this node. And then that means you're at risk to these numbers changing and then like violating the heap invariant, which is like this number has to be bigger than, or it has to be less than these numbers. Is that like any questions about that? So you can run this example through your head, and it's good to show the whole sort of like point this question is trying to get across is that when you like lock a position, like when you can no longer change a position, it's kind of bad because all of the things around you could change, and it could change in ways that make your current like item a bad item. Yeah? Okay, so then what about number 4? Yeah, so number 4 is good. Why? Because again, it's like you're not locking anything. You're sort of just sinking down. So every position, every node that you visit still has a chance to change. It's like the good flat rate way to think about it. And we are going to run out of time, so what I'll do is I think I can just record this and then post number 2 and 6, number 2 and number 5, and then yeah. Okay, let's do graph theory basics. So we're not going to do number 2. This is out of scope. Take 170 if you want to figure out how to prove this. It'll probably be in your second homework assignment. Okay, so graph theory basics. they're just asking us for a brief description on how to solve the following
Okay.
graph problems. And we're going to provide a worst case runtime that's bounded in theta notation in terms of the number of vertices we have and the number of edges. And then a WUG is a weighted undirected graph. So first they're saying find a path from node S to node T in a strongly connected directed graph. So the key point here is that it's strongly connected, which means that a vertex in the graph can reach any other vertex in the graph by taking some path. So that's the definition of strongly connected. You might be tempted to say first, it's like, oh, if I want to find a path to something, I should run Dijkstra's or I should run A star. You don't really want to do this because you're not looking for a shortest path. And Dijkstra takes like v times e log v time. And that's not, or v plus e log v time. And that's not really ideal if you're not looking for a shortest path. What I'm trying to say is that we can find a method that does it faster. So when we're trying to find a path from node S to T in a strongly connected graph, what we can do is actually just run some type of search on it. So we can visit, so let me draw first like a strongly connected graph that's directed. A, B, C, and then B can reach C, C can reach B.
I have to get spells that aren't in my
Great. Oh, let's say, let's say, let's make our graph look like that. So A, B, D, A, C, B, D, B, D, C, A, C, A, B, D. Okay, so yeah, this is a strongly connected directed graph because every vertex has some path to every other vertex. So when we want to find a path, we can actually just run some type of search algorithm. The reason for this is because our graph is strongly connected, which means just like starting at any node means that you're gonna, if you run DFS or BFS, you're gonna visit every vertex because there exists a path to every one of them. So for example, if you run DFS here starting at A and we break ties by alphabet, we're gonna take this edge,
What is this?
and then we're gonna take this edge, and then we're gonna take this edge. Now notice how because the graph is strongly connected, we can find a path from A, and the DFS tree is giving us a path from A to every other vertex. So if we want to go from A through C, we just go A, B, D, C. Is this the shortest path? No, because we could just go from A to C, but it is a path. So here we're going to either run BFS or DFS starting at S. Now, how do we recover the path? Well, we can do this by making every vertex that we visit remember the edge that it came from. So here we can tell B, hey, your previous node was A, and then we can tell D, hey, your previous node was B, then we can tell C, hey, your previous node was C. So we just run BFS and DFS up until we hit node T. So until T. And then we can backtrack to find the path. Now, the worst case for this is, well, what if we wanted to find the path to C? We actually had to visit every vertex. So to do that, the worst case is going to be B. So that makes sense here. But then we're also going to have to account for E because we iterate through all of the edges inside a graph. So what if, remember like your runtime for GFS is not just all the vertexes, it's also the number of edges because you consider every edge on a vertex when you visit a vertex. You don't necessarily take every edge, but you do have to iterate through all of the adjacent neighbors of a vertex. So that's why we have the runtime of theta b plus. Okay, let's do number 2, which is determine if a cycle exists in a directed graph. So when you're faced with these kinds of graph problems, especially for determining if a cycle exists, we can determine if a cycle exists if we know that like the same node is reachable from itself by taking a path, right? That's like definition of a cycle. So for example, if I added this edge here, this would be a cycle because A can reach itself by taking a path that's of length greater than or equal to 1, well greater than 1. So if a cycle exists in a directed graph, what we can do is that we can exploit this nature of being able to find like a path to yourself by using some kind of search, like some kind of search algorithm. And in this case, we can use either DFS or BFS. And the reason is because DFS and BFS have a special property, and that's that if you start DFS at node A, you will get all vertices reachable by A. And to kind of gain some intuition for this, we're gonna go and walk through DFS starting at A. So when we start DFS at A, I'm gonna draw the call stack. So we're gonna do DFS. So the call stack is just like the order in which I call DFS on nodes. So when I do DFS on A, that's one call. And then the DFS on A gives a second call to DFS on B because there's an edge from A to B. So this is what our call stack looks like so far. Now, a way I can implement DFS is that if I call DFS on a node, and if that node is already in my set of visited vertexes, then I can just ignore it. So for example, now that we're at B, we're going to call DFS on A. And that's going to tell us that there's a cycle actually, because inside this call stack here, we have visited A and then B and then A again, which means that there's a cycle. So if we do DFS, we'll say that there's a cycle if there is more than one vertex, there is more than one occurrence of a vertex. There is more than one occurrence of a vertex at the call stack. Now this call stack is very important because here we have a cycle because our call stack is A, B, A, and then A is like, oh, I'm already in the set, so it returns, and then B returns because it has no more children or has no more neighbors, and then A returns. So then our call stack becomes like nothing. So the reason the call stack is important is because if we just said, oh, if you ever visit a vertex that has been visited before, there's a cycle, it's not necessarily true, because if we have a graph that looks like this, and we run DFS, what's going to happen is when we do DFS of A, and then DFS of B, B is going to just return, and then A will return. And then in our DFS algorithm, we're going to pick the next in alphabetical order unvisited vertex, and that's going to be C. And then when we call DFS on C, we're going to call DFS on A again, but even though there are two calls to DFS of A, is there a cycle? No, this graph is acyclic. So that means only in like the active call stack, if you run into the same vertex twice, you'll have a cycle. So like in this case, this doesn't mean that there's a cycle because there's no path from A to A that's greater than 1. It just so happens that C has another edge to A, but because C is sort of like separated away from B, there is no cycle. So that's why we have to maintain a set that is the call stack and not just a set of like all the vertices we've ever visited if we want to do cycle detection.